Hi, my name is Nassim Nicholas Taleb, and I'm currently with the Tandon School of Engineering. I'm a former trader, and I'm going to be talking about how to play with Mathematica when you want to tinker with probability. How to just use it as a play, as something for amusement, and at the same time get deeper and deeper and deeper into probability problems. Thank you for inviting me. So this is 22 years ago. My book, Dynamic Hedging, using Mathematica. As you can see, it's been a long way since. Everything is drawn using Mathematica, all the graphs. And you can see this is done by Mathematica. It was not very attractive at the time, but it was, for me, it was very attractive. Okay, I didn't know, that you can have all these functions that we have today. So I've been living as a derivatives trader using Mathematica. But the good thing about it is that when I became a trader in my early 20s. And when you become a trader in your early 20s, you don't know a lot of theory, or whatever theory you studied at school is the kind of thing you try to forget right after the exam. So I didn't know a lot of probability. So I've picked up probability, as the French say, on the tas. So in other words, while doing it. And it's a complete different approach to probability from the one you would get by sitting in a classroom taking lectures from someone who has never been exposed to the same risks. So it's sort of like learning to ride a bicycle by spending 7 or 8 years being lectured at, okay? So, and instead of just being given a bicycle and falling a couple of times. So 22 years later, 96, this is 2018, a new book comes out, The Statistical Consequences of Fat Tails, using Mathematica. Now look at the difference. You see, all these, look at these graphs, this histogram with a transparent part here. Beautiful, okay? This is Mathematica. And not a lot of fluff, not putting a lot of fluff, some coloring here. So the aesthetics have changed greatly. And of course, 22 years from now, with the third book, technical book using Mathematica, okay, we're going to look back at this period and say, oh, why did he do it this way? Okay, so it'd be 3D, but I think the things have stabilized. So this is what I've been doing. So now I'm going to try to talk about the tinkering aspect, how one can discover properties just using a computer and playing with probability, or either you go to a casino, become an addicted gambler, and casino is not good enough because casino has Gaussian payoffs. But you can create on a computer and play with all kinds of non-Gaussian payoffs. So the main thesis of this new book is as follows. When you go to fat tails, the properties are very different. And why are the properties different? Because the law of large numbers and the central limit theorem, when they work very differently from theory. You see, a mathematician dealing with probability knows what happens at n of 1 and knows at infinity. We live somewhere in between. And when you live somewhere in between, there's some things that become very weird. Okay, there's some payoffs that come they are very different. So I'm going to talk about these things using, of course, a method that I didn't copy from Stephen Wolfram, because I did it myself as a lecture student by opening a Mathematica workbook and programming. Say, okay, when you want your food, you want it cooked on the spot, okay? Here we're going to do something similar, but with some shortcuts. So let me start with something commonly known as the central limit theorem. Everybody talks about the central limit theorem, and you ask people to define it, they all define it properly. They just don't tell you how fast you get to Gaussian. Now, what is central limit? Let me show you. Very simply, let's take a uniform distribution, the thinnest tail distribution, or the simplest one. And let's do a histogram of that distribution, okay? With n of 1, look what I got. Should I make it bigger? Window magnification a little bigger. 125, okay? I'm sorry? 150? All right. Okay. This is the Monte Carlo with 1,000 of a uniform distribution. Okay. Now I add two variables, and look what I got. Very quickly, I got a triangular distribution. Because think about it, you see, you have much, you can get one. To get one, it's very easy to get one. Any combination, half of 1.5, 0.2 of 1.8. It can give you give you one. But then to get 2.0 or 0, you see, you got to get 2.0 and 0 or 0. You see, so for the sum, to get, so you got to triangle very quickly. And then now, of course, by n of 6, you pretty much have a Gaussian. So I'm summing up a very small number of observations, and I got a Gaussian with, this is the central limit. All that very simple. The condition is that to have a finite variance, IID is recommended, required, sometimes not required. So they have these rules, and everybody in statistics assumes that if you have an n that is 30 or so, then you can talk about converging to a Gaussian. True? No. You eventually converge to a Gaussian, but at different speed for different distributions. Okay? And let's see how that works with a different distribution. Let me take the gamma distribution. Okay? And let's use 1. This gamma distribution, 1. 2. You're not in a triangle yet. 3. 6. Okay, it still doesn't look like a Gaussian. It's skewed at 6. And you can go on. Eventually, it will get to a Gaussian, okay? Rather quickly. It will start looking like a Gaussian eventually. And of course, at infinity, they all look like a Gaussian. Now, let me take a distribution, a Pareto distribution, with a tail exponent of 2. And let's do the following. This is how it looks like, not a Gaussian. This is at 6. For 1, this is how it looks like. You always have a very large deviation somewhere here. And if you, of course, ask Mathematica to show all observations, then of course, sometimes you have the thing going all the way here, you see. This is very, very compressed. So you have an outlier in that. And eventually, this will become Gaussian, technically. But it would take not maybe, let's see, at 30. It's going to take some time. So let me do 20. It may take several million observations. How many million observations? Aha, let's stop here and go to a bigger problem yet than a Gaussian. Have you heard of something called law of large numbers? Very simple. By tinkering, we're going to try to figure out what this law of large numbers is about, okay? Because practically, central limit is optional for statistics, okay? You could probably do without or with a more complicated central limit called generalized central limit. And it's not necessary for statistical inference. What is necessary is the law of large numbers, okay? For science, you need to know the mean. You agree? All right, so let's say things, again, in the literature, you do not have any information as to what n is required. It tells you n of 1 or n of infinity. So let's take, let's now, with the ln look at the following situation, okay? There is the distribution, the most commonly known is not the Gaussian. The most commonly used is which one? Sorry? Pareto 80-20. Simply because people talk about it on the media, stuff like that. You know, the newspaper, it's easy to understand. 20% of the people in Italy own 80% of the land, and so on. Okay, 20% of programmers do 80% of the work. 20% of the money in trading comes from 80% of the people, and 80% from 20. Okay, so So let's say now, let's see how that law of large number works with that Pareto distribution 1.14. And it has a mean, thanks to Mathematica. I don't have mean is 1 over alpha minus 1, okay, which is a mean of 8.14, okay? All right. Now let's run an average. We have 30 observation. Let's start with 30 observation. Sorry? R run the varied Pareto. It's not defined. Okay, there we go. We got a mean of 3.32. Okay? Want to try again? 579. We know what the real mean is, 8.14. Now, what is the probability of having a single observation at or above the mean? Very low. You see, these distributions are weird. Most observations are below the mean. You agree? Okay. Now let's look at the thing. I just wrote a paper on that. And strange enough, I mean, it's like nobody thought about it, okay? Which tells you the following. How much more data do you need for a Pareto, for an equivalent variance distribution? A Gaussian. How much more data do you need for a Pareto? Someone give me an idea, intuition? 5x? Who said more? Sorry, how much did you say? 150 more, he said. How many? More, 1 order of magnitude more? 10 to the 15. To get the same error on the same mean deviation, all right? Okay? Now, how do you discover that? By trying to figure out what the hell this law of large number is, okay? So let's look at the Gaussian, R1 random distribution Gaussian, and let's look at the Gaussian here, okay? How you converge to the mean of the Gaussian. Let's make it 10,000. No, that length the A1, sorry. Okay, look at the Gaussian. It's so smooth, no distribution, not single observation can mess it up, okay? Let's compare to the, and the Gaussian, this Gaussian has a high variance. No matter how much I raise the variance, let's say I go from 5 variance to 15 variance for a Gaussian, multiplying the variance. Okay, it delays you a little bit. Okay, not much. Okay? Now let's compare. You know what, let me, given that I don't like the blue color that comes with Mathematica, plot style red, particularly that it's justified in this case. Okay, this is a plot range all. Okay, there you go. This is the mean for a. This is what the mean does for, and even if we went to 10,000 for Pareto 80/20. Okay. So, the point is, of course, you go down. For one, you go down a square root of t, and the other one, you go down at a very, very different exponent. Okay. So, okay. Now these things. Now you may tell me this is trivial mathematically. Once you think about it, it becomes trivial. Okay, but you don't think of these things when you do. My idea of skin in the game is that you don't think there's something I call the blue lumber, the green lumber problem. And it's there's a story of a trader, a person who decided to get rich trading green lumber. So he bought every book on green lumber. He knew everything about green lumber, did every statistic on green lumber, every model on lumber. Okay, he knew everything. And then he had to write a book, What I Learned Losing $1 Million. Okay. And then he reported that there was a fellow pit trader who always made money with it. And then one day he discovered that that pit trader did not know that green lumber was freshly cut lumber. He thought it was lumber painted green. So the thing is, so from the outside, what you need to know, so it doesn't mean that the person didn't know anything. It means that from the inside, by tinkering and playing with something, you get a complete different story from the one you have on the outside, you see. So this is why you start with probability, you play with a Monte Carlo simulator. If you don't play with a Monte Carlo simulator, you'll never figure out. You're going to have a green lumber problem. So, and this, okay, so I've been doing this for years. And of course, you start getting intuition, for example, about what happens to the smoothness of random variables. This is a normal distribution using the bar chart, okay? Look what happens when you look at it. It is not scale invariant in the sense that if you look at it from very far away, if you zoom in, if you make it longer and zoom in, it would look smoother, you see? But the distribution we had before, a fat tail distribution, will never look smooth. You see, it will never look smooth. Once in a while, you're going to get a big jump. It will never look smooth. And if you extend it, it looks the same at all scales. Now, of course, on average. And if you extend it, probably will have a jump that goes way above 1,000, whereas the other one will hardly ever go above 3. So these things are visual. So number 1, CLT. Number 2, LLN. So you can start ranking the speed of convergence of distributions based on, how they work. And effectively, you can do analytical work. And to show you how you can do analytical work with Mathematica, I have, for everything I write, I have something on a side called Aid to Book, where you can do analytical work with Mathematica on a side. But it's not as much fun, of course, as Monte Carlo, because Monte Carlo will surprise you, you see? And they are beautiful functions you can use with Mathematica that we were writing longhand before. And then, of course, Mathematica started adding a transform distribution. You get a characteristic function. And then with that, you can invert Fourier. You can do things. You can do a lot of analytical work with that stuff. So there are a lot of little things we can do with Mathematica. Now let me talk about another intuition that, again, so from here on, I have a book, a mathematical book, published a lot of papers. It's a collection of papers. So a lot of papers in journals on mathematical properties of fat tails that came from very stupid observations discovered playing simply with that, Monte Carlo generator. Okay, so this is what I owe to Mathematica, but I owe other things, something else. Let's talk about the p-value problem. Okay, the p-value problem is, let's go back to the lecture, Wolfram conference demo. The p-value problem is as follows. Okay, here I have correlation. Let me start with correlation. I have 2 random variables that are completely uncorrelated. 0 correlation between the 2. And I have 18 variables for each. Okay? Let's do it, simulate it now. Okay? What do you expect the correlation to be between these 2 variables? You expect it to be 0. Okay? Very good. Let's see. So let's do A equal random variate. You pick a distribution. Someone picks a distribution. Sorry? Exponential is not exciting. Sorry? No. Okay. So let me use. Sorry. Let me use the simplest. Okay. Normal distribution. Sorry. Normal distribution. And let's say 18 variables. Okay. And B equal. Okay. All right. Now, what's the correlation between A and B? Okay, let's see. Are you sure? 42%. okay? Okay, so this is a problem of that's something that doesn't, this is very elementary. We know, and actually there's an explicit distribution for this in dimension 2, okay, the correlation distribution. And in dimension n, it's called the Marchenko-Pastur, which is on Mathematica, okay? For thin tail, not for fat tail, okay? For distribution of random value in the matrix. In expectation, you have 0, but no sample should deliver anything close to 0. But as you lengthen your sample, what do you get? You approach 0 at square root of n. This is well known. So let's do here a very simple distribution of correlation. Now, this is really 101, and I think Fisher knew about it 100 years ago. Okay? The problem is anyone who uses, I give a class, if someone uses any statistical package, so these packages that allow you to use a lot of data, automatically, I mean, I'm not allowed to brutalize students or be nasty to them, but I act as if the person has committed a huge sin. If you have not written your own equation, you cannot talk about correlation. That's because, or you have to play with it. So this is where you see that people can play with the system. Okay, we're still at correlation, not at p-values yet. Okay, that it's a random variable. Correlation is a random variable, and let's do here table. How many? Let's do 1,000. Histogram. There you go. So the correlation will be on average 0, but has a distribution. Okay. All right. People start to get it because visibly we have test statistics for that. But now comes the current replication crisis in psychology. If you apply the same reasoning to p-values, identical phenomena will deliver different p-values. Okay, you get what we have today, the replication crisis, with a bonus. What is the bonus? Is that if I'm taking the distribution of the maximum of random variables, okay, let's say now I have to choose between a lot of correlation. You see? Choose a lot of correlation. Then I have distribution of the maximum. It's called p-value hacking, and I have a paper called on the properties of p-value hacking. So, but I discovered that tinkering. I just took p-value, say, what's that shit, p-value? What does it mean? Okay, define it, the random Monte Carlo, and then it was all over the map. Okay, so this comes from tinkering, and let's see how I tinkered with p-values. This is the distribution of p-values that you get from tinkering. And to speed up instead of running it, if the p-value, the true mean, is something like 12, 60% of realization will be below 0.05. On average, you're going to get 12. On average. But it's highly skewed distribution. You don't have, you're going to get something in 40 once in a while that will bring it up. And most observation will be below the true p-value. So when I see someone with a p-value of 0.05, I laugh. Because I say, okay, they tried 2-3 times, they got a 0.05. The real p-value may be 25 or not even. So now, I don't know if you know what happened in psychology, but papers don't replicate. And also there's something, evidence of p-value hacking, because you look at how many papers have p-value of 5, a huge number, nothing at p-value of 4 or 3, and then some with p-value of 1. Okay. Now, how can we remedy this? By being skeptical about any metric and quizzing people. So anytime you discover something, you just do immediately a Monte Carlo. Now I'm facing in genetics something called the 4-population test. So I'm trying, someone sent a paper, said, do you want to be involved? I said, yes. So they sent me something with numbers. Okay. So, you know, so I went and I actually posted the Mathematica on Twitter, the 4-population test. The first thing you do is you run a Monte Carlo. You say, what's your n, what's that? And this is your distribution. So if you have 0.2, you're okay maybe. But if you have 0.1, if your statistic shows 0.1, no, you know, try again, okay? Or find something else to do. So this is where the value of tinkering comes. And again, it's as stupid as riding a bicycle versus learning, you know, taking lectures, okay? Keep riding a bicycle. I guess I'm okay, so I can keep going. Okay, great, thanks. So, okay, so let's continue now with this is my lecture, Wolfram conference demo. Okay, so you can also play with things with Mathematica, but there are functionalities. If you want to do conventional probability, there is a big problem. You've heard of Fifi, which is, or I don't know how you pronounce it. I don't think anybody knows how to pronounce it. But coming out of the Twitter of President Trump. And there was a quiz at the Indian Statistical Institute. Okay, how much should you type before you get a Fifi? And effectively, I just went in, you put the transition probabilities, okay, and then you get this thing of Fifi, and then you can know how long President Trump has to try to, or someone has to try to get it again. And you can mitigate it. You can make it how long someone has to try to find a word that sounds, you know, like this, or you know, you can make it, and that it's just a matter of adjusting the probabilities. Okay, so this is there's some things you could do. Other and of course, the most beautiful function in Mathematica for me to understand is of course the Monte Carlo simulator. And I remember the days when you could only randomize 0, 1 on Excel spreadsheet. And you had to do all these transformations to get a real distribution. And this is where you learn probability. Is a Box-Muller transform, other Dorner transform, or Zolotarev to have a stable distribution. But and the intuition you get from that is huge. But also, now continuing with intuition from Mathematica, you can play with, this is the stable distribution. You can play and figure out how parameters are affected, how you can make a distribution more fat-tailed. No, this is more variance. This is more skewed. These distributions, by the way, it was impossible to work in the old days because they don't have a density. Stable distribution class only has density supposedly for Cauchy, for the Gaussian, and for, I think, the Levy, which is, you don't want to hear about the Levy, okay? And here we can figure out what you fatten the tails, how things are, and build intuition just by playing with these functions. Manipulate is a great function for that. What happens when you change the parameters of a distribution? Incidentally, I discovered one thing here, and I'm going to share, is that although they say that the distribution has no closed form or near closed form, there are special situations where there is a closed form, whose alpha of 3 of 1.5. And the trick is, a lesson I learned is to always use fractional, okay, on Mathematica, because that's where you get surprises from tinkering. So this distribution, the ARI function, being something that effectively there's a lot of function, and then you can play with functions. Now let's continue with playing with Markov chain and quizzes like that. The second most important function for me is tuples. Why tuples is important? Can someone say why? Sorry? You're exploring. No, because you can see all the combination in front of you. So for example, I do tuples. There you go. Sorry, no, ABC. Sorry. Quit. you can see the combinations in front of you and start. I mean, it's a brute force exercise, or you can see it here, exhaustive or non-exhaustive. Okay, and then you can play with combination of random variables. That's another trick for solving problems. So you just get the intuition by brute force via tuples, and then later on start looking at discrete distribution to fit it, and then later on a continuous distribution. And it's quite powerful. Finally, a trick I did, you discovered in trading, was Monte Carlo. There's a trick. Okay, in the old days, when computers were not yet, computers are practically things designed for video games now, and for whatever it is. So it's sort of like help us get mathematical function faster, but that's not the purpose. So, but in the old days, it was very hard to do numerical integration, and very hard to do a Monte Carlo. So you had to be very stingy and very efficient. Today, instead of having more and more difficult equations, you just buy more computer power. Spend $15 more on computer power instead of $75,000 in research money. Okay, so something figured out in sampling is, if say I have a function here, I have a function that starts here, and it's in a Taylor distribution. So there's only 3% of my Monte Carlo will cover that function. Okay, say like an option, out of money option, basically. 3% of my Monte Carlo run will affect that option. So one trick where you can use an analytical method along with brute force is you shift the distribution, okay, where the center becomes at your point, 102, 2 standard deviations away. I shift the distribution. I do my Monte Carlos. Okay, I've saved. I can save. Instead of having 3% of my observation, now I have 50% of my observation at or above that point, and then do a change of measure, probabilistic change of measure, and that way I get, like, I'm multiplying my sample size or hugely, and I get a lot more accuracy for cheap. So these are some of the techniques that you can do with, and you can still do it. Still saves money. Still saved is still okay. So let me conclude, and then we'll take Q&A. The whole thing that I can bring to the table, because you guys are more sophisticated than me when it comes to whatever it is. Okay, the only thing I know is to transfer from practice to theory, and the value of trying to transfer in that direction. And in the absence of practice and probability, you're not going to go to a casino, okay? And I don't know if you've been to a casino, but you notice it's addictive, and people who spend a lot of time in a casino, they start having, they look sallow, and then they have like all these marks under their eyes. So it's painful, okay? You just go to a cafe, have a good cappuccino, and play with Mathematica. And then you discover properties, okay? So thanks to these intuition, now I have I have a bunch of papers on how to translate what happens with n of 100, how do you compare distributions based on these metrics. And of course, the p-value thing also came to me immediately when I said, what the fuck is this? Sorry, what on earth is this p? All right? You hear p-values in papers. What? Okay, let me see. Okay, this is how they define it. You run them on Monte Carlo, and then you see, they're full of crap already. You don't have to wait for the replication. The replication crisis, for those who don't know, is that I think only 40% of psychology papers replicate, and those that replicate have a much weaker effect. Okay, they haven't tried in economics yet, but I think 0 would replicate because they use Gaussian methods and, of course, Gaussian methods. Now, you can do this in higher dimension. It's in my book. I'm not here to talk about my research. I'm here to talk about how to tinker with Mathematica. Thank you for listening to me.